All right, so on Friday, right? We went, or you went over 2, 4, which is complex numbers. So all the things relating to imaginary numbers. So the foundation is the I is equal to the square root of -1. Okay, square root of -1 is obviously not a real number, so we call it an imaginary number. So I raised let's just stick with the foundation. The I squared is equal to -1. Okay. For part of this, we treat I just as though it's a variable. So if we're adding two things that have I on them, we treat them just as though it's a variable. That changes when you've got I raised to a higher power than 1, because then we have to simplify it. So when you look at number 1, I would simply just distribute this, and I'd get 9I times 5, which is 45I, minus 9 times 3 is 27I squared. And then you will never leave I raised to a higher power than 1 in your work, because it's not simplified. So we're going to say I squared is really -1, and we'd multiply the -1 times the -27, and this becomes positive 27. And then if it had said write in standard form or complex form, that means the I always comes last. So this would be rewritten as 27 plus 45I. And the 27 is your A, or your real part, and the 45 is the B, and 45I would be the imaginary part. All right, then we go to 2. And as is, you cannot simplify. The very first thing you're going to do is take the I out. So the I has to come to the outside, which gets rid of the negative inside the parentheses. Inside the square root. And then 20 would be 4 and 5, so 4 gets square rooted as 2. This becomes 2I square root 5. And 45 is 9 and 5, and 9 gets square rooted, and a 3 comes to the outside, so this is plus 9I square root 5. And only because they both have an I and they both have a square root 5 can we combine this into one term, 11I square root 5, which can also be written as 11 square root 5I. If you're going to write it like the second way, you have to make sure your I is not underneath the root. So I'd actually prefer it the first way, so that you're more careful, because the I can't go underneath the square root. But the second part is also correct. And if it's in standard form, if it's multiple choice, it's actually how it will be written. Questions on that one? All right, number 3, now we've got I in the denominator. That's having an irrational number in the denominator. It can't stay that way, so we rationalize by multiplying by the opposite. We multiply by the conjugate, which is the same expression with the opposite sign. So in the numerator, I would FOIL it out. I'd get 25 plus 5I plus 5I plus I squared. This gets combined to be 10I. I squared becomes -1, and my numerator is 24 plus 10I. And then the denominator, you could FOIL it out, or there's a shortcut when you're multiplying conjugates, and the shortcut is A squared plus B squared. A is the number that is by itself the real number, so that would be 5 squared. B is what's in front of the I, which would be a 1 this time. And then I'd get 25 plus 1, which is 26. So my denominator is 26. And then when we write these in standard form, you could either simplify it first and then split it, or you could split it and simplify it, but you're going to do both. So this becomes 24 over 26 plus 10 over 26I. And 24 and 26 are both divisible by 2, so this becomes 12 over 13, and 10 over 26 becomes 5 over 13. So we want to simplify it, and we want to write it in standard form, which means the I comes last. Yep.
Could it be 5I over 13, or does that be 5 over 13 times 5?
No, like if you put I in the top, that's fine. If it was multiple choice, it will be written next to it, but if it was open-ended, it would be fine. Allison. It can, but if it's multiple choice, it will be split. Yeah. As long as you reduce it. If you don't reduce it, you'll lose points. But if you rewrote it like instead of like 5I over 13, this would also be fine. Yep. We good so far? Okay, so when we get to 4, I also want to go over a quick trick that's going to help you like testing, like standardized testing wise, okay? When you go to solve for a quadratic, so I can try to factor this because that's obviously for most of us, the easiest way to solve a quadratic, okay? But obviously in this section they weren't factorable, which means your backup is the quadratic formula. I don't want you to have to complete the square on something like this. Could you do it? Yes, but that would be really messy, okay? So your backup is the quadratic formula. But there will be standardized test questions, especially on your PSAT and the SAT if you're a junior getting ready to take that, where it will literally ask you what type of solutions are there to this question. And you could go through the full-on process of having to actually solve it and then see what it is, or you could use this shortcut. And this shortcut is using something that's called the discriminant. The discriminant is what's underneath the square root of your quadratic formula. So negative b plus and minus the square root of b squared minus 4ac over 2a is the quadratic formula. The discriminant is the part that's underneath the square root, which is b squared minus 4ac. And there, if you do that, if you just did b squared minus 4ac, there are 3 different outcomes you can get. The first is that this is a positive real number. And if that happens, then there are 2 real solutions or roots. Whoa. Okay, the second option is that it is 0. If the number b squared minus 4ac is 0, then it means there's only one real solution. And the last is that it's a negative number. If it's a negative number, there are 0 real solutions. And there are 2 non-real or imaginary solutions. So standardized tests, especially the SAT, that when they changed it, they started to put these kinds of questions in, where you don't even want to go all the way through trying to figure out your answers. Okay, what you want to do is just figure out what would be under the root. If what's under the root would be positive, that means I would add and subtract a positive square root. If what's under the root is 0, you'd be adding and subtracting 0, which means there's only one answer. And if what's under the root is negative, you'd be adding and subtracting I, which means there are non-real roots. So if I just looked at this example and started with that, b is negative 4, so negative 4 squared minus 4 times a times c is 16 minus, this is 12, and 12 times 16 is 192. This is obviously going to be a negative number, which means there's going to be 2 non-real roots. If I did 192 minus the 16, I get negative 176. So to figure out what kind of root it is, I didn't even need to figure out the 176. I just needed to know it was negative. That means that there's 2 non-real roots. But we are going to actually find this. So I'm going to keep going. So negative b plus and minus the square root of b squared minus 4ac all over 2a. And my a is 16, and my b is negative 4, and my c is 3. So I would get negative 4, which is 4, plus and minus the square root of, and I already did this, negative 4 squared minus 4 times 16 times 3, all over 2 times 16. So I get 4 plus and minus the square root of negative 176, because we already did that work, over 32. Now I know the negative means I'm going to bring an I to the outside. That makes that a positive 176 inside now. And then 176 is even. 2 goes into it 88 times. 2 goes into that 44 times. 2 goes into that 22 times. 2 goes into that 11 times. And then for each pair of numbers, one of those numbers going to the outside. So this 2 brings a 2 to the outside. And this pair of 2s also brings a 2 to the outside. So I've got 4 plus and minus 2 times I, so 4I times the square root of 11, because 11 didn't have a pair, over 32. And then I can either split and then simplify, or I can simplify because all three of these spots have a number that's divisible by the same number, which is 4. This would be 1, 1, and 8. So I get 1 plus and minus I square root 11 over 8. Or 1/8 plus and minus the square root of 11 over 8I. So a standardized test, multiple choice, is going to have it written as the second one. Open-ended, I would take either one. Questions? So the only thing that's not on this warm-up that was also in the notes is like if you're multiplying two square roots that are negative. Okay, and this is a common mistake people make, which is why I want to go over it real fast. This does not equal the square root of 50. I cannot multiply out what's underneath. The very first thing you have to do is take out the I. So it'd be I square root 5 times I square root 10, which becomes I squared times the square root of 5 times 10, which you can then multiply out to 50, but you're going to want to break it down anyways, so you might as well leave it separate. And then there's 2 5s, so a 5 goes to the outside. It'd be 5 times I squared, which is -1, times the square root of 2. And this becomes -5 square root 2. Questions on that one? Oh, and there's one more thing I want to go over, which was the higher power. So this, it's on the review. We'll go over it again tomorrow. But if you have an I to a higher power, like something like I to the 51, what you could do is actually, let's start with 50 first, and then I'll do to 51. What I could do is like groups of 2, right? Because every I squared is a -1, and I can figure out how many -1s there are. But it would take you a long time with something like 50. They could put 132 up there. You'd still have to be able to do this process. So for me, what I do is I rewrite this in terms of an I squared. So I write I squared raised to the, so what would I have to multiply 2 by to get to 50? 25. And then that means that there's a -1 inside that parentheses, because I squared is -1. And there are 25 of them. If there's an odd number of -1s, what is my answer? -1. If the even, right, if that was 26, so if it said I to the 52nd power, I would rewrite this as I squared raised to the 26, and that would be 26 -1s, which would make that what? A +1. So if my original exponent starts even, I'm going to cut it in half, so divide it by 2. That's how many -1s there are. Now, if my original exponent is odd, for example, then the very first thing I'm going to do is take off an I. I'm going to rewrite this as I to the 42nd times I. If it starts odd, there will always be an I in my answer. I just have to figure out if it's a positive I or a negative I. So I take that I out, and then I do the same thing to that I to the 42nd that we just did. I squared raised to the, so 2 times what is 42? 21 times I. There are 21 -1s, which means, is this a positive or a negative? -1 times I. If I had started 45, first thing I would do is make it 44 times I. I would rewrite I to the 44 as I squared raised to the 22nd times I. I squared becomes -1, and there are an even amount of -1s, so this is just positive I. Questions? Again, that'll be back on your review, but it is on your test, so you got to make sure you know how to do it. All right, we're going to jump into the notes. for 2, 5. So 2, 5 pulls together 2, 3, and 2, 4. It takes what you did in 2, 3, finding your roots, and then it will find the remaining roots, and some of these remaining roots are going to be complex. That's the idea behind 2, 5. So we start with what's called the linear factorization, okay? If f of x is a polynomial of degree n, where n is greater than 0, then f of x has precisely n number of roots. What this means, and we've talked about it already, is that if x is raised to the 7th power, there are 7 roots, or 7 solutions, or 7 x, well, not necessarily x-intercepts, roots, solutions, zeros. Up to this point, all 7 of those roots would have been real numbers. But what we're going to get into today is now there's going to be a mix of real numbers and non-real numbers. So if you look at something like this is a complete factorization of something, or a linear factorization of a function. We're going to combine together real answers that are rational, like -3 and +1/2. Real answers that are irrational, like the square roots. And then also complex answers that are going to involve I. So there's going to be real roots that could be rational or irrational, rational being whole numbers or fractions, irrational being like square roots that are not perfect squares. And then complex imaginary zeros, meaning we're going to mix in I's into these. All right, how many zeros are in this function? 3. That's it. Easy stuff, like just to figure out the number. Example 2 says solve the function. So if you're looking at A, there you've got lots of options. One, it's not factorable because it's not a minus. Okay, so I could use my even root property. I could also use the quadratic because it's x squared. On B, you cannot use the quadratic because it's x to the 3rd. But on A, what I can do is say 0 equals x squared plus 36. Subtract the 36. And then square root both sides, and now I've got my I plus and minus the square root of -36, which would be 6I. Then I go to B. 0 equals x to the 3rd plus 25x. What's the first thing you're going to do? Good. Factor out the x. X squared plus 25. And then I'm going to split and solve because it's not factorable from there. And I get x equals 0. X squared would equal -25. And x would equal plus and minus the square root of -25, which is plus and minus 5i. Because it's raised to the x to the 3rd, we should know there's 3 roots. So it is 0, -5i, and +5i. If you're listing them, let's say this is an open-ended question and you're listing them, you can certainly put plus and minus 5i. But if it's something like on WebAssign, it wants you to list out the zeros, you're going to have to separate that out. Good so far? All right. Example 3, now we're getting into different kinds of functions. Well, it's still quadratic, but I can't use the even root property on A. X squared minus 3x plus 1, I'd have to use my quadratic. So my A is 1, my B is -3, my C is 1. So -3 is +3, plus and minus the square root of b squared minus 4 times a times c all over 2 times a. 3 plus and minus the square root of 9 minus 4 over 2. 3 plus and minus the square root of 5 over 2. So this is 3 minus square root 5 over 2 and 3 plus square root 5 over 2. And then we write it as linear factors. So x minus 3 minus root 5 over 2 and x minus 3 plus root 5 over 2. And then we're going to do the distributing of the negative, and we can't leave the fraction, so we're going to move this to the front of the x. So I get 2x minus 3 plus square root 5, and 2x minus 3 minus square root 5. Now, if you had time, let's say you had time on your test or whatever it is, you could actually FOIL that back out and make sure you get your question. All right, then we go to B. B is not quadratic, so you cannot use the quadratic formula on it, but B is factorable. This is the difference of two squares. So I'd get 0 equals 16x to the 4th minus 81, and that would be 4x squared plus 9 and 4x squared minus 9. With me so far? Are either of those factorable from here? Yeah, that second one is also the difference of two squares. So 4x squared plus 9, and then 2x plus 3 and 2x minus 3. So the zeros from my second set of parentheses are negative 3 over 2 and positive 3 over 2. I have those two. There are 4 total based on my exponent being 4. So I also have to solve the left side, and it's not factorable. I'm going to set it equal to 0, subtract the 9, divide by 4, and square root, putting a plus and minus in the front. So x equals plus and minus the square root of negative 9, which is 3i, over the square root of 4, which is 2. So my 4 zeros are negative 3 halves, positive 3 halves, negative 3i over 2, and positive 3i over 2. When I write them as linear factors, minus a negative 3 halves would become positive, minus a positive 3 halves, minus a negative 3 halves, and minus a positive 3i over 2. And then each of those, the 2's got to move. So this is how it would be written as a product of linear factors. All right, so this is the big one, and this is kind of like what will happen on your test on the calculator portion. So I'm going to teach you how to do this in a couple ways, but one is, it says find all the possible zeros of the function. So remember from last week, possibles are plus and minus the factors of the last over the factors of the first number. That's the first thing we're going to do. Then we're going to find the actual roots. So if we didn't have a graphing utility, then I would have to literally test all the possibles until I found one that worked. But that would be a waste of our time testing-wise. So instead, you will get given a graphing utility, and it will allow you to find one of the real roots. Then it says to write the polynomial as a product of linear factors. So we're going to have to factor it out or find all the remaining factors, put it in the parentheses to show it as a linear factor, and then find the x-intercept. So I actually will find the x-intercepts first, then write it as a product of linear factors. And then in this case, it says use the graphing utility to verify. On your test, you would actually have the graphing utility to help you find one of the roots. So first thing I'm going to do is find the possibles. The first number is 1. The last number is 16. So plus and minus the factors of 16, 1, 2, 4, 8, and 16 would all go over 1. So it would be plus and minus 1, 2, 4, 8, 16. These are your possibles. It's also going to ask you to figure out the number of positive and negative roots using Descartes' rules. So this question kind of on your test builds in all that stuff. Now it says use the factorization to determine, find the actual roots. So if I didn't have my graphing utility, I'd have to try those roots using synthetic division until I found one, okay? But instead of wasting time to do that, we're going to use the graphing utility. So I'm going to graph this function. I'm just going to say we're going to run out of time. All right, we know where to go. You're literally going, stay left. Stay with us if you can, but if not, you're staying left of the, wait guys, we'll go together. With finding a zero, and this is what it will be similar to on your test. So if I look at the graph, there's actually only one real zero on that graph, and it is at 2. If I didn't use this, I'd have to try all my possible routes until I found one that works, and it would have been 2. Then what I have to do is reduce this function using that 2. So I'm going to put 2 on the outside, and I'm going to use synthetic division. 1, -4, 8, -16, and 16. Bring down the 1, multiply it, put it in the next column, and add it. Multiply it, put it in the next column, and add it. Multiply it, put it in the next column, and add it. Multiply it, put it in the next column, and add it. And I'm expecting a 0 here because we just said this is a root. So now I'm going to take what's left. The 4 gets the x, the 2 gets the x squared, and the 1 gets the x to the third. So this is x to the third minus 2x squared plus 4x minus 8. And sometimes, like this example, it's factorable. If it's not factorable, then it wouldn't start as x to the fourth. You would either have to find another root, which there's not another real one in this case. So it would have started as x to the third. We would have reduced it to x squared. And if that wasn't factorable, we'd use the quadratic, which is what's going to happen in your test. We'd use the quadratic to find the remaining roots. Yeah?
But on the test, like, are we going to have to do a question like that, like, without a calculator?
No. All right, so then I'll group it. I'll take out the x squared, x minus 2, take out the positive 4, x minus 2, and I get x minus 2 and x squared plus 4. So I do have another real root, it's 2, but it means that just had a multiplicity of 2, which should make sense because my graph bounced at that point. And then to solve x squared plus 4, I would subtract the 4, plus and minus the square root of -4, plus and minus 2i, which makes sense why my graph only had 1 0. So positive 2, negative 2i, and positive 2i are my zeros. 2 would have had a multiplicity of 2. The linear factorization would be x minus 2, x minus 2, because there's 2 of them, x plus 2i, and x minus 2i. So when I list my linear factors, I have to include anything that was a duplicate. Because when I FOIL this out, it has to give me my question. So the process will be very similar for your test. It will start as an x to the third though. So an x to the third, you'll find one root using your graphing utility. You'll use synthetic division to reduce it a degree. It will now be x squared. And then those remaining roots are going to be imaginary because they won't be on your graph. And you'll use the quadratic to find your remaining roots. Okay? So similar at the beginning, a little twisted at the end. The last couple of slides on here, I'll finish. Okay, so conjugate pairs. If a plus bi, where b is not 0, meaning there is an I in my zeros. If a plus bi is a 0 of the function, then the conjugate is also a 0 of the function. I's come in pairs. So if 2i is one of your zeros, you automatically know negative 2i is also a 0. If negative 10i is a 0, then positive 10i is also a 0. They always come in pairs. Otherwise, your polynomial will have an I in it, and that's not a polynomial. Polynomials can't have i's. And if I said 5i was one of your zeros, then we would add negative 5i. If I said 2 minus 3i is one of your zeros, then we would add 2 plus 3i. We would automatically know its conjugate is also a 0. So example 5 says, find a polynomial function with real coefficients that has the given zeros. So this is going back to 2-2, like part 2 of 2-2, where if I gave you the zeros and you wanted the polynomial, you're going to list these after x minus. Now the catch this time is that one of these has an I in them, okay? So if a is 3 and 3 plus I, what do you automatically know is also a 0? 3 minus I. So then if I wanted to write out the polynomial, it would be x minus 3, x minus 3 plus I, and x minus 3 minus I. You don't have to do those parentheses as long as you remember to distribute the negative. So it'd be x minus 3 minus I, and x minus 3 plus I. Now we get to FOIL it out. Here's what you don't want to do, just like with your square roots. Don't do the first two first and then multiply that times the third one. Group together your i's. Because if we multiply these out, the i's are going to go away. It makes it a lot easier, okay? So I'm going to multiply out first the second and the third parentheses. X times x is x squared. X times negative 3 minus 3x. X times I, positive xi, or ix, that doesn't matter. Then repeat with the negative 3. Negative 3 times x. Negative 3 times negative 3. Negative 3 times I. Then the negative I. Negative I, x, God bless you. Negative I times negative 3, positive 3i. Negative I times positive I, negative I squared. Now, if you've done it correctly, everything that has an I should go away. So a positive xi and a negative ix cancel each other out. A negative 3i and a positive 3i cancel each other out. And negative I squared becomes minus a negative 1, which becomes plus 1. So I get x squared, combine your like terms, minus 6x plus 10. And then I'm going to multiply it times x minus 3. So distribute the x to all three, x to the third, minus 6x squared plus 10x minus 3x squared plus 18x minus 30. And then the last thing I'm going to do is combine my like terms. X to the third minus 9x squared plus 28x minus 30 equals f of x. Say again. No. One, it won't because it has eyes. It won't. But two, if it was rational, it would factor back to your question. Yeah, but it won't factor because it has eyes. Sure. We won't go all the way through B, but what I do want you to do is at least set it up. So if negative 2, 5 minus 3i are roots, what else is a root? 5 plus 3i. So I would get x plus 2, x minus 5 plus 3i. I distributed the negative, and x minus 5 minus 3i. And then I would first multiply out the second and the third, the ones with the i's, and it would get rid of your i's. And then I would multiply it times x plus 2. There's on the test like one. On the homework, I think there's one. Yeah. There's no duplicates of any types of questions because there's so much content. Questions on that? Okay, so now how do we use it? It says using one complex zero to find the remaining zeros. So let's say your function has complex zeros, meaning it has I, and you don't have a graphing utility to find the real roots. Then what you're going to do is take the one I that they gave you, add its conjugate, because now there's two of them, they come in pairs, FOIL them out, and then divide the original function by our quadratic, which means long division because it's quadratic. Okay, so now we're going to review. We go back to 2, 3. So it says use the given zero to find all the zeros of the function. So my 0 is 1, 0 is 5i. That means what else is automatically a 0? Negative 5i. So if I want a polynomial there, I'm going to write x minus 5i times x plus 5i. And I'm going to FOIL it out. X squared plus 5i minus 5ix minus 5ix minus 25i squared. These go away, and I get x squared. This is negative 1. Changes this to positive, plus 25. So shortcut is also a squared plus b squared. The a is the x, the b is the 5. Okay, so now I have my two imaginary numbers, k, or my polynomial. So I'm going to take my original cubic one and divide it by what we just found. So 2x to the third plus 3x squared plus 50x plus 75 divided by. Now look what you're dividing by. Do you have all the terms? It's in decreasing degree order, but what's it missing? An x to the first, so I'm going to add in a 0x. So x squared plus 0x plus 25. So what do I have to multiply x squared by to get to 2x to the third? 2x. I'm going to multiply it times all three terms on the outside. 2x times x squared is 2x to the third. 2x times 0x is positive 0x squared. 2x times 25, positive 50x. Change your signs and add. First one cancels out, which it's supposed to do. 3x squared minus 0x squared is 3x squared. Positive 50 and negative 50 cancel out, but I give the 0x because I still need the placeholder. And I bring down the 75. And I repeat the process. So what would I have to multiply x squared by to get to 3x squared? Positive 3. Multiply it, 3x squared. Multiply it, 0x. Multiply it, positive 75. Change your signs. Cancels, cancels, cancels. Remainder 0, which is what I expect to happen because I want to know what my remaining root is. And if it's a root, my remainder will be 0. So my 3 zeros here are 5i, negative 5i, and what I'd get by setting my quotient equal to 0, which is negative 3/2. If it wanted it in full linear factors, it'd be x minus 5i, x plus 5i, and 2x minus 3, plus 3, sorry, plus 3. I set my last factor equal to 0, so the quotient equal to 0.